What we would like to do today is take one of the applications of the weak force. How do we use radioactivity for power production? And that's of particular interest for people in aerospace engineering because NASA is using radioactivity to provide power for the probes in outer space. And right now on Mars, one of the probes, in fact, uses the isotope Plutonium-238 to produce power for the experiments that are exploring whether there is some form of life on Mars. So let us start by sharing here. And in that case, we go to the chapter. We'll jump from radioactive processes. We'll come back to them later on. But we go to the space applications of nuclear power. And in that case, we look at radioisotopes power production. Those of you who would have interest in NASA, in fact, some of the students who participated in that course that we are taking now, NPRE 402, have been hired by NASA. So if you think about joining NASA, which is a very challenging, interesting process, make sure you try to interview them when they come to the campus. Compact devices using radioactive isotopes have been used for a long time. They were designated as systems for nuclear auxiliary power. It started in 1956, and the acronym for that is SNAP, S-N-A-P. The first SNAP device was the size of a grapefruit. It weighed 4 pounds and generated a power of 2.5 watts. And it delivered 11.6 kilowatt hours of total energy. When you multiply watts by hours, that's energy. And over about a year, 280 days, it provides power. This is a great advancement over having to use nickel cadmium batteries, because in that case, what was weighing only 4 pounds replaced something that would be 700 pounds if it's nickel cadmium batteries, and the cost of launching materials into space is some kind of prohibitive. So you could see that that was of great interest. The isotope used in that at the time was the polonium-210. Polonium-210 is an alpha emitter. It emits alpha particles. And we'll see that you can get the energy from those isotopes to generate heat, and then you can transform the heat into electricity. The production of electricity from radioactive materials of radioisotopes is designated as radioisotope thermoelectric generators. RTGs is the acronym for it, and you may like to explore the NASA site. Just go there and explore how the RTGs are being designed, manufactured, and used in general. Without those RTGs, we wouldn't have been able to launch missions like the Apollo missions to the moon, the Viking missions to Mars, the Pioneer, Voyager, Ulysses, Galileo, Cassini, and the Pluto New Horizons even to the outer solar system. If you have a chance to visit Chicago, the Museum of Science and Technology, you can go to the site, the part of the museum. By the way, it's free on Tuesdays. If you find your way there on a Tuesday, entrance is free. You go to the Apollo mission and you'll see that the Apollo missions to the moon left on the surface of the moon one of those RTGs generators. The RTGs for the Pioneer 10 spacecraft operated flawlessly for 30 years, 3 decades, until the spacecraft signal became too weak in 2003. The Voyager 1 and 2 missions operating on RTG's power since their launch in 1977 are reaching interstellar space out of our solar system. And the United States launched 26 missions involving 45 RTGs or radioisotope thermoelectric generators over a 40-year period. So why do we use them, those radioactive sources of power in space? There are 5 situations where you need them. When the satellite orbits pass through radiation belts, such as the Van Allen radiation belts that surround the Earth, the radioactivity there from electrons and protons is so high that it can destroy any photovoltaics or solar cells. So the radioactive isotopes become a substitute. Operations to the moon or Mars, where long periods of darkness require heavy batteries to supply power when solar cells would not have access to sunlight. Especially on Mars, for instance, you have storms, dust storms that could shield the photovoltaics in the space probes. A third situation is missions in opaque atmosphere like Venus. Venus is surrounded by clouds. Solar cells would be useless because of the lack of light below the clouds. At far distances from the sun, for long duration missions, if you use fuel cells, that would use hydrogen as a fuel, or if you use batteries as well as even solar arrays would be too large and too heavy, and then you run also a risk of their breaking down during their deployment. You would need maybe in the upper reaches of the solar system, you would need a solar array the size of a football field, and it doesn't make sense if the mission would fail. And some of the deployment of the solar arrays, in fact, did not occur as planned, so radioisotopes become a choice. Heating the electronics and the storage batteries in the deep colds of space. We'll look at a problem that considers how cold space is as we proceed further. The space in general is at minus 240 degrees Fahrenheit. So in that case, in the deep reach of the space, your electronics and storage batteries have to be heated. You cannot allow them to to freeze to minus 245 degrees Fahrenheit in general. All right, so how do we use a design a radioactive isotope to be used in space applications? We go back to what we wrote or derived in our last chapter about what we defined as activity of a given isotope. So we are not going to consider the decay as a function of time. Let's start from the point where we are putting it together. So the number of atoms of a given isotope, let's call them n sub 0. When you multiply that by the decay constant of the radioactive isotope, the decay constant, as a reminder, is the natural logarithm of 2, 0.6931 divided into the half-life, and you multiply it by n sub 0, then in that case, this is the initial activity. N sub 0 is the initial number of atoms, and we can calculate this from Avogadro's law again. We keep coming back to Avogadro's law, which tells us that N sub 0 would be the mass of the isotope, G sub 0 in grams, divided into its molecular weight. That gives us the number of moles, and each mole contains Avogadro's number, 0.6, 10 to the 24th power of atoms, nuclei, or molecules per gram molecular weight. And this is in fact one of those radioisotope heating units. And now, if we talk about radioisotope heating unit, it has its own acronym again, that is RHU. It weighs about 40 grams. Here is a little tiny piece of plutonium 238. In that case, the size of a penny. You see a penny here, and it's a very lightweight, really. It's also only 40 grams when you add to it the graphite container and shield. Why graphite container and shield? Because plutonium is extremely toxic. You worry about failure in the launch process. So many rockets upon launch basically exploded. So you don't want that plutonium 238 to be dispersed in the Earth's atmosphere. So you enclose it into that graphite kind of a container. And graphite, as you know, can take very, very high temperatures. So you prevent it from being dispersed. So the plutonium-238 is placed inside the graphite shell into the container, and then it has a plug on the top of it to protect it at launch time. This weight of 1.4 ounces can generate for us 1 watt of power. Well, if you need 10 watts of power, oh, you place in 10 of these little containers. So 1.4 ounces of weight is the same as 40 grams. So it's a very, very tiny amount that can produce but heat in that case. So we call it a radioisotope heater unit. Why do you use the heat? First, if you use photovoltaics, you store the energy in batteries, and on the surface of Mars, the temperature goes below 0 at night, so you need to keep your electronics heated. Or later on, we'll see today that you can take that heat and through thermoelectric conversion, energy conversion, we can turn that heat into electricity to power the different units on the spacecraft. This is more detail of that radioisotope heater unit. You could see that plutonium-238 is surrounded by insulators, and the fuel pellet itself, actually, it's not metallic plutonium-238, it's plutonium-238 dioxide. So it's a ceramic. Being a ceramic, it can also take very high temperatures, and then it is enclosed in the heat shield and the insulator and the whole plug of graphite that we have seen. Plutonium at room temperature, remember this is the isotope of plutonium, plutonium-238, not the plutonium-239 that is used in weapons or the plutonium-239 used in nuclear reactors. This is produced by a special process that I'll show you. That is the isotope 238. 238 emits quite a bit of alpha particles. The alpha particles slow down in the metal to the point that that metal glows out red at room temperature. This shows us a plutonium-238 disk. It glows red hot from its internal heat generator. What is of interest to us in the design of these devices is the specific activity, or the activity per gram of the isotope, in that case, whatever it is, polonium-210 or tritium or plutonium-238 or strontium-90. There's a whole list of isotopes that we can use in these types of applications. And they have a great promise in the future for MEMS devices. That's of great interest to our mechanical as well as our electrical engineers, not just the aerospace engineers. MEMS stands for micro electromechanical systems. So that would be part of the new field of nanotechnology. So the isotopes, say, of tritium, if it starts emitting electrons for us, and no gamma rays. So gamma rays would be a source of radiation that we need to shield against, but the source of electron means that you produce a current. So it acts like a battery, but at the microscopic level, at the atomic level, not just the size of centimeters, but that's at the size of really, I would say, millimeters. The specific activity then is the activity per gram per unit weight, and we'll take the CGS system of units. So the activity itself is the decay constant multiplied into the number of atoms or nuclei, initial number divided into G, the mass of the isotope. Remember, the unit of activity that we defined last time was the becquerel, abbreviated as BQ. 1 becquerel is 1 transformation per second, or 1 disintegration per second. Now, if you take the number of nuclei here multiplied by the activity, and then multiplied by the energy release in each radioactive decay, let's call it E here, in million electron volts, then we can write an expression for the power, specific power, or power per unit mass. So if you substitute E here in million electron volts, and becquerel is these integrations per second, you'll find that now you have million electron volts per second. Oh, that's power, energy produced per unit time per gram. So that would be specific power. I suggested that N sub 0 can be obtained from Avogadro's law. So let's do that. Let's substitute for N sub 0, G, the mass of the isotope, multiplied into Avogadro's number divided into the molecular weight. G divided by M itself is what we call 1 mole, or 1 gram molecular weight. So if you substitute for N sub 0 G multiplied into Avogadro divided by M, then we have an expression for the specific power as a function of the mass of the isotope. So let us plug in that number here, and we find that the specific power, million electron volt per second power per gram, is E, the energy of the radiation emitted by the isotope, multiplied into lambda, the decay constant, multiplied into Avogadro's number divided into the molecular weight of the isotope. And you can express million electron volt per second, this is a unit of power obviously, into a more convenient unit for power, which would be the watts, or joule per second. And the conversion factor is at 1 million electron volt per second is equal to 1.6 10 to the minus 13 watts. So if you multiply that power, specific power density into 1.6 10 to the minus 13, then the power density would become watts per gram. So in that case, the design equation is very simple. The watts per gram is 1.6 10 to the minus 13. The energy of the isotope, the decay constant of the isotope, Avogadro's number divided into M. Now these are, remember here, I have added here TH. TH is stands for power that's in the form of heat. The alpha particles emissions heat up the isotope and can get it to glow red hot, as I've shown you in the photographs earlier. So in that case, you need to cool it. And the cooling itself can transform our thermal energy into electrical energy if we multiply that P prime by the overall thermal conversion process. So this, if you multiply by the thermal conversion, overall thermal efficiency of whatever process you are using to convert heat into electricity, then you add watts E per gram. And notice obviously that watts thermal and watts E are very different quantities. And as engineers, when we talk about power, we have to specify what is the form of power we are using. And in our tests, I'll watch how you are going to be careful in differentiating between the different forms of power. It could be mechanical power, it could be aerodynamic power, say in wind turbines. Here, this is thermal because it's heat generation. And then here it's in the form of electricity. We're going to use that very simple relationship really for the design, as I'll show you in a moment, of how much material, say, you need to produce a certain amount of power of the radioactive isotope. But let us first talk about plutonium-238. Plutonium-238 is an isotope of plutonium that's very, very different from the isotope of plutonium, plutonium-239. And the plutonium-238 is produced in nuclear reactors by isolating the isotope of neptunium-237. Remember, we wrote in the decay chain of the different decay chains that one of the decay chains, the man-made one, starts with neptunium-237. How do we produce neptunium-237? It occurs in existing reactors when a fast neutron, so this is a reaction that does not occur with the thermal neutrons or the low energy neutrons. It happens with high energy neutrons interacting with the isotope of uranium, the abundant isotope uranium-238. It's an end-to-end reaction, meaning that the uranium-238 absorbs a neutron and emits 2 neutrons, turns into uranium-237. Uranium-237 is unstable. It emits a negative electron and becomes neptunium-237. So in the fuel, spent fuel from nuclear power plants, NASA goes and chemically separates, because it's a different isotope here, 93 electrons rather than 92. It can be chemically separated from the spent fuel from nuclear reactors. Then that neptunium-237 is taken, placed in a research reactor and irradiated again. So when it absorbs a neutron, it turns into neptunium-238, emits a gamma photon, and then the neptunium-238 emits a negative electron and turns into plutonium-238. Notice it is not plutonium-239, the isotope used in weapons or for power production, because we burn it in existing reactors. So let us just estimate what is that specific power if we are using the plutonium-238 isotope. To do the design calculation, we go to the chart of the nuclides, and we determine what is the half-life of plutonium-238. You find that its half-life is 87.74 years. So in that case, we can plug that number in the equation for the specific power of the isotope. Here, lambda is 0.6931, the natural logarithm of 2, divided into the half-life in years. But you have to be very careful here, because the activity was calculated initially in becquerel, and that was disintegrations per second. So that 87.74 year, when you calculate the decay constant, is 0.6931, the natural logarithm of 2, divided into 87.74 years, multiplied by 365 days per year, by 24 hours per day, by 60 minutes per hour, by 60 seconds per minute. So you have to check really and be very careful with the units. So the energy emitted by the isotope from the chart of the nuclides also is 5.544 million electron volts. So we plug here that 5.544 for the E, the constant comes in right here. And then we are left with the molecular weight in the equation. And for plutonium-238, if you want to be exact, it's 238.0495. You can take it as an approximation as 238. And then Avogadro's number, 0.6 10 to the 24th power. If you look at the handbook of chemistry and physics, Avogadro's number is usually listed as 6 10 to the 23rd power. We are going to use 0.6 10 to the 24th power for a reason. Later on, when we define cross sections, we'll find it's easier to use it in that format. Plug in the numbers and do the cancellations, and discover that the specific power for plutonium-238 is 0.56 watts per gram, 0.56 watts thermal per gram. So let's say if it's a half a watt thermal per gram, and you want to produce 1 watt of power, so how many grams do you use? It's very simple. It's the inverse of that P prime. 1 over P prime, gram becomes grams per watt. So you need 2 grams of the plutonium-238 to produce, say, 1 watt of power. You want 100 watts? Oh, okay, you need 200 grams. It's a very simple relationship using our design. It's simple, a very simple design equation for that case. Can we only use plutonium-238? No, there are many, many, many other isotopes that we can use. And that's what I mentioned, the field of nanotechnology can be really take advantage of the fact that these isotopes can emit different forms of radiation that can be heat that we turn into electricity, or guess what? We can get electrons right away. For instance, if you use nickel-63, the isotope of nickel-63, it is a pure beta emitter. I say pure here because it emits only negative electrons. So you have a source of electrons, so you have a source of current. in that case, at the nano level, at the atomic level. And it doesn't emit gamma radiation, so you don't need to shield against very penetrating radiation. We'll see later that gamma rays can penetrate maybe 1 meter of concrete. And in that case, you find that the half-life is 100 years, and it can last longer, obviously, for space applications. That would be interesting. But because it has a long half-life, you'll find that it has also a very low energy per disintegration. That's 0.067 million electron volt. Compare this to the plutonium 238, the energy per disintegration was 5.56. So that was a million electron volts. So it's quite a big difference. See here, 5.5 million electron volt per disintegration. Nickel 36 emits beta particles at a much lower level. So how much of a power density, a specific power density can we get? Let's plug in the numbers. Instead of 5.54 here, we have 0.0567 million electron volts. The half-life is 100 years. Again, we turn that into seconds, and then the atomic the atomic weight is 62.92967. So you'll find that because the energy of the beta particles is lower than the one for plutonium, you end up with a power, a specific power in thermal power of 0.0224 watts per gram. All right, so we have a collection. In fact, you can use tritium too. Tritium is the isotope of hydrogen. It has a 12.34 years half-life. Maybe that would be a nice problem to give you as an assignment. And what is the design equation? What we want to know is what is the mass of the isotope that would produce for me a certain amount of power. So if we go and calculate that P prime, the number of watts thermal produced per gram, then if I specify the power that I need, say I need 100 watts, I divide that into the specific power, watts thermal per gram, and watts cancel, and we get grams. So the design equation is extremely simple. It's just the mass of the isotope to produce a certain amount of power is the power that you need, thermal power, obviously, at that point, divided into the specific power of the isotope, the equation that we spent some time deriving today, that equation right there. Very simple design equation. Of course, you have to take into account what is the mission time in the choice of the isotope. If the mission time is in the range of tens of years, the plutonium-238 has been chosen to be the best one. If it's a matter of just 1 year, polonium-210 has been chosen to be the best one. All right, we have thousands of isotopes available to us. So how do we choose or select a given isotope for an application in space? Engineering, definitely you'll find that it is not useful to take an isotope of uranium-238 to produce power. It doesn't produce much power at all because its activity or the radiation that it emits when the half-life is too long in the billions of years is very low. So practically, you need to choose an isotope with a half-life between 100 days and 100 years. And that reduces the number of isotopes available to us from the 1,000 that I talked about to 100 only. And then it's also engineering-wise not practical to use a power that is lower than 1/10 of a watts per gram. If you choose that criteria, you'll find that 100 isotopes is reduced to only 30 isotopes. And you can choose among them and come up with very interesting designs in our future in nanotechnology and in MEMS type of devices, micro electromechanical systems. And that is something, an active field of research. That's why I'm covering it, that chapter, and bringing it to your attention. If we have 30 isotopes left, the attention has concentrated on only 8 isotopes. So I list some of them here. I mentioned tritium. Tritium is an isotope of hydrogen. It's used, in fact, in our liquid crystal displays, LCD displays. So your laptop computer, your phone uses a tiny amount of that tritium imported from Canada, from their CANDU type of reactors. And so it's a big business for them to provide it. Without the tritium, we would not have the color, the red color and the phosphors that we use on our LCD displays. Now, tritium is very interesting because it doesn't emit gamma radiation, and we'll see later that gamma radiation is extremely penetrating, and it emits only negative electrons, beta minus emissions. Its half-life is 12 years, can last basically a good life time, and the specific power is 0.26 watt thermal per gram. So it's 1/2 the specific power of the plutonium-238 isotope. I have added to the list here silicon-32. It's also interesting for MEMS applications because it doesn't emit gamma rays. Phosphorus-32, phosphorus-33, sulfur-35, scandium-46, but then, or cobalt-60, but then these start emitting gamma radiation, and you have to shield against that gamma radiation. Some of them have different half-lives, practical lifetimes. Tritium is 12 years, but then if you need to use something that has a very short half-life, say in a medical application, 14 days, that's phosphorus-32 or sulfur-35. Cobalt-60 can emit beta particles, but also gamma radiation. And nickel-63, again, is a very useful one because it doesn't emit gamma radiation. Its half-life is 100. A here stands for annum. Annum is Latin for year. All right, so when you say A here, you see A, that's a year. A gas, krypton-85. The Russians in the space application did not use plutonium like in the United States. Instead, they used strontium-90. Strontium-90 is a fission product, so they separated it from the fuel of nuclear reactors. It is also a beta emitter. It doesn't emit gamma radiation. It has 29 years half-life, very useful. However, what they did not realize is that strontium-90 itself decays into another isotope, which is yttrium-90. And now yttrium-90 emits gamma radiation. So over time, a radioactive isotope kind of device using strontium-90 eventually starts emitting gamma rays. And accidents happen from that perspective. At the time of the old Soviet Union, they placed buoys, sources of electricity for airplanes, and in the Siberian desert, if you want to call it. It's a huge extent of land. And over time, the strontium-90 decays into yttrium-90. Hunters there came in and sat next to that heat source because it was hot to warm up. And of course, they got an exposure of gamma radiation. So in that case, strontium-90 is not favored as a source of power for radioisotope devices in general. You can think about yttrium-90, ruthenium-108, cesium-134. Cesium-137 is also a fission product, but it emits gamma radiation. Promethium, terbium, thulium, all of these are isotopes that we can think about using, even gold-198. One of our favorite is thallium-208, and that has a half-life of 3.7 years with no gamma radiation. The ones that have been used widely are polonium-210, plutonium-238 that we used. However, plutonium-238 is useful in space, but not on Earth, because it emits alpha particle, yes, but it also emits gamma radiation. So its use in space is fine. There are no humans around it. And it also undergoes spontaneous fission. It fissions all by itself, producing neutrons in that case. Plutonium-241 also has been used, as well as americium-241. It emits alphas, gamma, and undergoes spontaneous fission. This one is used in smoke detectors. So in that case, do not place a smoke detector over your bed in general. The forms that are, for those isotopes that emit gamma radiation, you need to shield. And the best shield in that case is a heavy element. We'll see that gamma rays can be shielded against with heavy elements. So if you go to a hospital and you get an X-ray, which is electromagnetic radiation, but at the kilo electron volt or energy level, not the million electron volts we are talking about here, they give you some kind of a protection blanket that you place on your body to protect your vital organs against the radiation from the X-rays. In any case, the form of the isotope, the chemical form for plutonium-238, as I mentioned earlier, is plutonium-238 oxide. Some of them, the cesium-137 uses chloride, and strontium-90, to take a very high temperature, they use basically titanium oxide. So that's called strontium titanate, all right? And they have different melting point in that case. The plutonium dioxide has a very high melting point. So that's why it's suitable for launching into space in case of an abortion of the launch. It's not going to disperse itself on over the ground in general. So you find that these are gamma emitters. In that case, you need quite a thickness, 10 centimeters of thickness in lead against plutonium-238. But space is a very, very high radiation environment. The surface of Mars has a radiation environment, so they are used in space and on the probes on the surface of Mars. There are many commercial forms of the isotopes. Let's take some of them. Strontium-90 is strontium titanate that can take a very high temperature. And the plutonium-238 we mentioned is plutonium dioxide. So if you need the source of radiation for power production in a space probe, you have a whole set of choices here. In the case of strontium-90, which has a half-life of 28 years, that's what the old Soviet Union has used, you'll find that strontium titanate, strontium TiO2, has been identified as a suitable fuel form. It needs to reach a temperature of 1910 degrees Celsius to melt. And the way to produce it is very simple. You use solvent extraction on, spent fuel from nuclear reactors. You can isolate the strontium-90 from the strontium-89 from the fission products in general. Strontium-89 has a short half-life, 51 days, so it disappears very quickly, and you end up with the strontium-90. So that's why the old Soviet Union used it very simply. Well, as I suggested, the heat generation is a useful product. You keep your electronics in space heated up. They will not freeze, otherwise you cannot use electronics or batteries. If you know, like batteries on your car in the winter, if they are frozen, you cannot get them started. So it's more convenient to turn that heat also into electricity. And in that case, methods of energy conversion are used, several of them. One of them is a methodology of what we call thermoelectric conversion, and it depends on the Seebeck effect. You may have seen that in your physics classes in the lab, where if you have a hot junction and a cold junction, the Seebeck effect suggests that you get a current between the cold junction and the hot junction if you use specific materials that have different electronic work functions. In the case of radioactive isotopes, they provide us with a source of heat. So if you have a heat source here, you use solid state physics and NP, two NP's junctions. One N is basically stands for negative, and P stands for P. And in that case, you attach them to a surface in space. We don't have convection. There is no air to carry the heat. So in that case, in space, we depend on radiation to dissipate the heat. And as you dissipate the heat, you get a cold junction. So here, the radioactive isotope provides you with a hot surface, and the radiator in space becomes the cold junction. And now between the two, between the hot side and the cold side, you find that you generate an electric current. So you use the heat from the radioactive isotope at the bottom here with an NP junction, and you end up with electrical power generation. This is what we call thermoelectric conversion. And the way it would look like as a schematic from NASA, you had the hot shoe here. That would be the plutonium-238 isotope, or if it's in the Soviet Union, it would be the strontium-90 isotope, or other isotopes or other applications. You have the N leg here, the N junction, and you have the P junction. And then those two junctions now are coupled to a radiator. The radiator radiates the heat into space and provides the cold junction, and the current flows between the cold and junctions. So this is an actual picture of a radioisotope thermoelectric generator from NASA. And you could see the fins here, like some old motorcycles have been using fins to dissipate the heat from the surface of the engine. In that case, air-cooled engines. Some airplanes in the past also used fins on their propellers to dissipate the heat, and the dissipation in space has to be through radiation. It cannot be through convection. The vacuum of space is a vacuum. Radiation can propagate in it, but not, there is no convection there. Okay, so the main application in that case is space applications, but I foresee in the future a large field of application in nanotechnology or MEMS devices. So it's left to your imagination once you learn how to design one of these devices, very simple design process to use it in, for instance, a small engine that would go through the arteries of a person who has atherosclerosis, where the arteries are blocked by fat, and clear up the artery. That would be some kind of a dream for curing disease of old age. The whole concept of thermoelectricity depends on the figure of merit of the square of the Seebeck coefficient. That's a thermoelectric property of the material that's equal to the voltage produced for each degree of temperature difference. So if you basically have a beaker in the laboratory containing ice and one that contains hot water, you put a wire in between the two beakers, you find that you get a current of electricity. R is the resistivity of the thermoelectric material, and K is the thermal conductivity. And that's really what we call thermoelectricity. You see the R, the resistance of the wire, that's electrical engineering, and K here is conductivity. So that's thermoelectricity in general. It's a whole field of science by itself. The higher that figure of merit Z, the better the thermoelectric materials. Ordinary metals like copper conduct heat too well. Instead, semiconductors like bismuth telluride and germanium silicide make very good thermoelectric elements. And as I suggested, that is not pie in the sky. This is actually an engineering application. You could see here one of these thermoelectric generators used by NASA on the surface of Mars. This is, in fact, a replica of one of those thermoelectric generator. They call it the multi-mission radioisotope generator because initially NASA started by using photovoltaics to produce power on the probes to Mars, but then they needed batteries to store the energy in the night of Mars, and then those batteries would freeze. So they added heat generators to keep the batteries and the electronic from freezing. And then the photovoltaics got covered with the dust from the storms on Mars. So their efficiency decreased over time. So eventually now on Mars, they're exclusively using thermoelectric generator. They are not using photovoltaics anymore. So you can see here that it has fins to radiate the heat. So it can be used in space, not just on Mars. Nevertheless, on Mars, it's a useful thing because the atmosphere of Mars is very, very, very thin compared to the atmosphere of the Earth. So convection there is minimal. So they use radiation to dissipate the heat. That multi-mission design you could see here in more detail. You find that the thermoelectric modules there are surrounding the heat source at the center. So that would be the hot part of it, and the cold part is radiation into space. And this is from the NASA. And this is more of the detail where you have your, in that case here, the radioactive isotope and how the radiation is converted into electricity. There is another method of obtaining electricity from radioactive isotope. Remember, we called the previous method that uses a temperature difference between two surfaces. We call it thermoelectric generators. We can also use another energy conversion method that is designated as thermionic converters. So it's not thermoelectric, it's thermoionic, and thermionic basically creates ions. So you use a material in which by heat, you can separate the electrons from the nuclei in the atoms. In that case, you ionize the material, and one choice material is cesium. So if you heat up the cesium vapor, in that case, you can break the cesium atom into ions and electron. And once you boil that cesium, basically, the atoms, you find that your electrons start moving from the one side to the other, the hot junction heat, T sub H, to the cold junction, T sub C, and you find that you can have a current of electricity growing out in the in a load. So all you need is the heat in from the radioactive isotope, and then it is not waste heat, but it's radiative heat. So in that case, the material would be what's called the low work function collector, and the heat itself is generated by high work function emitter of the electrons in general. So that would be a thermoionic generator. And it looks like a light bulb here. You could see here, all you need is a cool surface and a hot surface to create a current out of a radioactive isotope. What if you need not just the watts level of power for instrumentation, you need something in the range of the kilowatts or 1,000 watts, then you can use basically conventional thermodynamics here. This is a SNAP-2 generator, as it's called. It uses a high-speed turbine. In that case, the working fluid is mercury. So you heat up mercury with a radioactive isotope, then you evaporate it, and then you condense it. And then you also use here now a sodium pump rotor, and you use a bearing that also uses mercury as a lubricating fluid. So you could see here mercury bearings, and the thermodynamic cycle, instead of using water and evaporating water, you evaporate mercury. You notice, of course, mercury is extremely toxic. However, in that SNAP-2 type of a generator, you can, well, using radioisotopes as a heating source, you can get 3 kilowatts of power. So in that case, use a high-speed turbine, use a mercury coolant, and an electric generator and pumps to produce 3 kilowatts of power. That is not the only method here. We also can use what's called the nuclear battery, a beta cell. And that is where, as the application micro electromechanical systems, MEMS devices, deserves really more exploration. In that case, it uses the simple principle of what's called the Mosley generator. All you do in that case is find a radioactive isotope, example tritium, or even a fission product that emits electrons. So that would be a beta emitting radioactive isotope. You collect the electrons from the emitter on a collector. And in that case, immediately you have a potential drop that can circulate in an outside element. It depends on the energy of the electrons in that case. So you can get very high voltage. So it's very suitable for power, for an electrical, for an accelerator, because the voltage would be high. Otherwise, you need to use technologies in which you reduce the energy of the electron by electron multiplication. Basically, if you get an electron with 1 kilo electron volt of energy, and you split it into, say, 10 electrons, each one of them would have 100 volt of kinetic energy. So in that case, you get basically directly the electrons in the outside circuit. And that again has been built and used. Other methods that people have been talking about is the piezoelectric generator, the optoelectric battery, and many other ideas are being used. The current ones are the PN junctions that NASA uses in its space probes. You have to shield in some of those isotopes like plutonium-238 against gamma radiation. And that suggests that a more promising use is isotopes that are emitters of electrons. So you generate a current, but not gamma radiation, in which you need basically very high thickness, at least during manufacturing, to shield against gamma radiation. So basically possibilities in that case is tritium, nickel 63, strontium 90, technetium 99M, prometheium 147, plutonium 238, curium 242, curium 244 are all interesting possibilities other than the low energy isotope in general. Some people came up with the idea of what's called the alkali metal thermoelectric conversion, and AMTEC. If you see the word acronym AMTEC, that's what it is. So it's left to the imaginations of engineers on how to use radioactive isotopes to produce power, particularly for space applications in general. So this is not pie in the sky. This is a picture of the Cassini spacecraft. And it's the size of a bus. And it was launched into space through the space shuttle. And look here, 1, 2, 3. This is radioisotope thermoelectric generators, 1 out of 3. And they are shown here to provide power to all the components, especially the communication satellite dish, if you want to call it satellite, to communicate with the Cassini spacecraft was sent, I think, to Saturn, one of the missions for it. I'll show you another one. Oh, here is a more detailed description of how you have the radioactive isotope, the hot surface, the heat source, I call it general purpose heat source at the center. And then you have the radiator fins at the outside. So this is the hot junction. This is the cold junction, the cold of space. Even in missions close to the sun, radioisotope thermoelectric generators have been used. One of them is used here with what I think is a Ulysses space probe. Yeah, that's Ulysses solar probe, because going very close to the sun, even though you have good photovoltaics at your disposition, but the magnetic fields there would spoil any photovoltaic electronics and solar radiation. So again, you'll find that an RTG also even close to the sun is a useful thing. The size of those RTGs is shown here. These are the hands of some engineers putting them together. Obviously, they haven't loaded the charge of plutonium-238 because in that case, they need shielding against gamma radiation. And other space probes, the Galileo spacecraft has been sent all the way out of our solar system. And you could see here, again here, radioisotope thermoelectric generator hanging up on a boom. It is kept away from the electronic equipment because in that case, the gamma radiation, as we'll see when we study about the effects of gamma radiation, would affect the electronics in general. But you could see it's used here two of one here and one here shown as basically radioisotope thermoelectric generator. So NASA has been using this technology to a great extent. Initially, as I suggested, the probes to Mars, this is the largest part of the space program now, determining whether there is some form of life on Mars, maybe there is one, is really the Sojourner. And it was sampling this a Martian rock here. You could see they have photovoltaics being used, but then if you use photovoltaics, you produce some power during the day on Mars, and then at night you have to store it in batteries. So they still use radioactive isotopes to provide heat, to heat up the battery, the energy stored in the batteries, and not get the batteries to freeze in the very low temperatures on the surface of Mars. This was supplemented, replaced later by the Mars Surveyor programs, and it needed, in fact, those radioisotope, but heating units, not generator units. The Spirit of Mars, you could see, have also large solar collector photovoltaics. And the problem with them is that Mars has an environment that's very, very stormy. So that's why the Mars looks red in the sky. And some people associated the redness of Mars in Greek mythology as being the god of war. It is really iron oxide from the surface being stirred up by the violent wind speeds that can reach hurricane speeds 100 miles per hour. So the dust deposits itself on those solar collectors, and basically their efficiency stops over time. Interesting trivia here is that NASA discovered that some of those probes that used photovoltaics came back into function. And the suggestion is that even though the winds deposited the dust on the photovoltaic collectors, another storm would come in and clear it up, and now it comes back into function. That is intermittent, that is not very realistic. So now in the science laboratory that NASA has on Mars, they are exclusively using Plutonium-238 as a source of power. It shows here how a very ingenious way of landing the probe hanging with basically rockets being fired to bring it to the surface of Mars in a way that doesn't destroy it. And these are pictures of it now sampling, well, not actual pictures. This is it shows us the experiments that were conducted in sampling the rocks. They had many, many experiments on that particular probe. So let us list them very quickly. The instrumentation that was carried is shown here. The cam, the mass cam, the REMS, the booms, ultraviolet sensors. And you don't see the photovoltaics anymore because all the power is being produced by the radioactive isotope plutonium-238. The interesting thing is that NASA is running out of that plutonium-238 isotope. So basically, they had an instrument for the entry descent. They called it the medley instrument, the Mars Descent Imager. It's called it MARD as an acronym. The Chemicam laser instrument. These are all experiments that are being conducted with chemistry and mineralogy, rover environmental monitoring, the REMS instrument, alpha particles X-ray spectrometer, APXX sample analysis at Mars. They call it the SAM instrument. So they had so many of those experiments amassed. And then they had cameras, of course, that brought us a picture from the surface of Mars. The latest rover on Mars is called the Mars Perseverance. And that one is shown here. No photovoltaics anymore, but much more sophisticated with a dependent, very high reliable power supply using plutonium 238. This is actually the actual rover or Perseverance before it has been launched to the Mars atmosphere. And basically, it is considered as a way of looking. This is the artwork on how that rover was brought to the surface of Mars, which is very interesting, high tech. And this is the actual picture of that rover being descending with the rockets on the top there to the surface of Mars. So we have cameras now that can provide us with very, very detailed information. Of particular interest in the latest experiment now on Mars is the development of a UAV, unmanned aerial vehicle on Mars. And that is shown here in the lab when they were experimenting on it. The problem is on Mars, the atmosphere is very thin. So for the electrical engineers, you would know that you need to provide very high lift. So they have basically two counter-rotating blades on their UAV on Mars, and they did fly it, in fact. So it extends the distance of the exploration process. So they had a very, very ingenious counter-rotating rotor blades to keep it flying. It's battery operated. It's almost like a helicopter here on Earth. So it's a twin blade helicopter. And there is interest in that mini helicopter that traveled with the rover. It's only 2 kilograms, and it performed, in fact, already the first power flight on some other worlds. So this is how humanity is extending its reach to other parts of the solar system. Here is a picture of Mars, and you could see it's a red planet, but in fact, Mars has two poles that are cold, so there is water there on Mars. We know it is, and the atmosphere of Mars is primarily carbon dioxide, very little oxygen. So any first settlers on Mars would have to produce their own oxygen. So that Perseverance experiment was trying to generate some oxygen for Mars, or we'd have to basically turn some of the water and frozen carbon dioxide on Mars and maybe terraform Mars to look like the Earth by maybe exploding some nuclear devices, evaporating the water and the carbon dioxide, creating a greenhouse effect that would heat up the surface of Mars and allow for life to emerge on Mars. That would be terraforming Mars. So this is part of humanity reaching beyond its very confined surface of the Earth. I have to conclude that chapter by saying that the use of power as heat or electricity from radioisotopes will continue to be indispensable for space exploration. As technology evolves, you'll find that we may have applications in nanotechnology, in microelectromechanical devices. At some point, for a manned mission to Mars, not only do we need to use nuclear energy for the rocketry that will get us there. In that case, the mission time would be only in the range of weeks rather than in the range of years if we use chemical rocketry. So the dream of reaching Mars and for humans is, and their urge to explore is a fascinating topic. In addition, because of lighter specific impulse compared with the chemical one, a nuclear rocket may in fact be used to propel the spaceship to Mars, reducing its travel time from a year to a few weeks or months. So it's not just that we need the radioisotopes for power for its first mission to Mars, but we also need the rockets that would get us there to use nuclear power because they have a a high specific impulse. So basically, specific impulse is the impulse per unit mass, specific is per mass, and that gives it a high acceleration. So if you have an 8-cylinder engine on a Volkswagen, you could see that it can accelerate real fast and get to its destination in a shorter time. I'll stop sharing here for that chapter and go to the chat room. If you have questions, the questions will be welcome. Ask them right now, the chat room. I'll make sure it's open right now. I'll give you today an assignment where you would design one of those devices for an application of radioisotopes in space applications. If not, we are ready to go and look at another very, very important application of the radioactive isotopes. In that case, you find that we are using them today, in fact, for medical applications. So we go back to our very interesting chapter on radioisotopes application, radioactive processes, and look at the process of food preservation by radiation. Now, this is a use of gamma rays or X-rays from electron beams to preserve food supplies. And the food science people, if you ask them, tell you that unfortunately today, we lose 30% of the food that we produce to spoilage, spoilage to bacteria, to fungi. And if we can supply a better food supply, increase it by 1/3, in fact, by controlling the spoilage of the food. And radiation allows us to do that, as I'll show you today. As we do this, we will study how much is the radiation or the dose of radiation that we give to a food supply to protect it from fungi and from bacteria. And that will help us define a second unit for the measurement of radiation. The first unit that we identified already was the process of the unit that we call the activity. The unit that we'll define today is going to be the radiation absorbed dose. So radiation has been used extensively today to also sterilize medical products, and hundreds of thousands of lives have been saved by, especially maybe during the pandemic, by using disposable syringes. And in the third world, unfortunately, it's still in some places they use glass syringes and steel needles, and they reuse them by boiling them in water. And boiling syringes in water is not enough to destroy viruses. So they end up with a spread of HIV and a spread of hepatitis C. An advice, if you find yourself traveling to a third world nation during the summer or maybe during any time of the year, to go to the McKinley Hospital, tell them that you are traveling abroad, and they'll give you a supply of disposable syringes. Those disposable syringes are made out of plastic, and they have been sterilized. It's a disposable syringe. They have been sterilized in the same way that food is being protected by radiation. Simply radiation sterilizes the plastic inside their boxes without using any heat. The radiation kills any bacteria or fungi. But what we are going to do today is explore a new industry. It is used extensively in Europe and Canada, but not in the United States. It will come to us for preserving the food supplies and extending the shelf lives. Why is that important to consider as a future technology beyond the sterilization of medical product? Is that basically the CDC, or the Center for Disease Control and Prevention, suggests that we get 48 million cases of foodborne illness every year. So almost 1/5 of us gets some what we call stomach ache or stomach flu. It's not a stomach flu. It's definitely one of the infections that we are going to study today that can be controlled with radiation. You'll find that we get 128,000 people hospitalized and 3,000 people killed every year from foodborne disease. That is unnecessary and can be avoided. This is as much as, in fact, what the victims of the September 11 event, and that caused the whole war. But so here there is a war that we need to launch on bacteria and fungi to really save the lives, unnecessary loss of life of 3,000 individuals in the United States. The symptoms that people encounter can be abdominal cramps, it can be vomiting, nausea, diarrhea especially. That's what people call, oh, I have a stomach flu. It's not stomach flu, it's diarrhea. And it can also cause fever. Serious cases that can kill people, especially in people who are compromised, the elderly or people in nursing homes, for instance. They're not just subject to the COVID-19 virus, but they can also be subject to kidney failure. And the foodborne disease costs apparently the United States $77 billion a year. And we can spend much less on protecting against the occurrence of that of these diseases. 1 in 6 Americans get sick from food every year. Imagine that. Well, we are about 30 people here together. So 1 of 6, so 5 of us, we get some form of foodborne disease in a year. The figures definitely are lower than those around the year 2000, but they're lower also from other parts of the world. But if we lose 3,000 people a year to foodborne disease, imagine third world countries where meat, for instance, is sold in open markets. It is not refrigerated. How much foodborne disease occurs right there? The known food contaminant that can cause illness in humans, the leader is salmonella. It causes about 28% of the deaths from foodborne diseases in general. You'll find that salmonella is so common that Walmart accepts ground turkey after tests, and they find about 50% of the sample have bacteria in them. It tells you that don't eat turkey unless it's really, really well cooked to kill the salmonella bacteria in it. The United States is expected to import half of its food by 2030, up from 20% in 2012 from China, Mexico, and Vietnam, particularly like fish, for instance, or shrimp. Quite a bit of shrimp is grown in farms in Vietnam, for instance. Basically, author Upton Sinclair wrote a book, The Jangle. It was a scathing book about the Chicago meatpacking industry, with workers falling into vats of boiling beef trimmings and other horrors. The next year, the United States Congress passed what's called the Pure Food and Drug Act. Act means a law, which proved basically ineffective. In 1938, after 100 people died from the antibiotic sulfanilamide, Congress passed the Food and Drug and Cosmetic Act, strengthening the FDA, the Food and Drug Administration. So we have the Food and Drug Administration as a federal agency, has the power to inspect, approve, or reject all food and pharmaceutical products. From the outset, though, the FDA lacked the resources to inspect all of the country's food products, and the food industry moved to fill that vacuum with private auditors in the 1990s. In some cases, companies producing food don't want to kill the people who eat their food, so they have their own private inspection. The first effort in preserving food, of course, was by salting the food. When you salt the food, you deplete it of the water, and in that case, the bacteria cannot grow in it. Hence, you have salted maybe different fish that you put in the water, and then you can start cooking it. You also can preserve food by adding spices. And you heard about the spice trade in the Middle Ages, where spices from the far reaches of the world were brought into Europe, and spices were as precious as gold. Then you also have the process of adding sugar. When you add sugar, you decrease the amount of water in confectionaries, and in that case, you reduce the growth of bacteria. But the great development, other than refrigeration, before refrigeration, was the canning of food. So when you can food in bottles and jars, dating back to 1810, it was perfected by a French confectioner making basically sweet stuff, Nicolas Appert. This expanded the scope of human diet and saved food supply in the 19th century until refrigeration came up in the 20th century. We wouldn't think about having food in your home now without having it refrigerated in general. It started with people having ice boxes, and you would have peddlers, in fact, going in the streets. You haven't seen that, nor probably your parents, where they get chunks of ice that you put in an ice box to keep the food really refrigerated. But now we have electrical refrigerators, and no home can really be seen in the United States without one right now. Cases of hemolytic uremic syndrome, HUS, and another more serious enterohemorrhagic E. coli. E. coli is Enterica coli. That's a bacterium that grows in our intestines, and it grows in the intestines of cows and the intestines of chicken. And when they're slaughtered, basically it contaminates the meat that we end up eat in general. The serotype STEC, they call it from Escherichia or E. coli, caused foodborne outbreaks before and carries genes that make it resistant to common antibiotics. So that is a very nasty mutation, the same as the mutations in our COVID-19, but that happens to bacteria, not viruses in that case. So we have two variants of the E. coli that are new, that basically are resistant to antibiotics in that case. So let us look at you can read more about the introduction here, but in 2006, an unprecedented array of products recalls occurred. E. coli 0157H7 in bagged spinach, that sickened 200 people in 26 states. There was salmonella in tomatoes, took a toll on 183 people in 21 states. Again, E. coli 0157H7. This is a new mutation in the E. coli bacteria. And its suggestion is that in that case, the idea of having eggnog around Christmas, which is eggs that haven't been cooked, should be out of your choice at Christmas. Also, the idea of eating sunny side up eggs should be eliminated, because those bacteria would survive on the surface of the uncooked surface of the egg on sunny side eggs. Eggs should be cooked on both sides if you want to avoid getting the stomach flu. It is not stomach flu, it is really a combination of bacteria. In the stores now, you can find that some food have that symbol on it. It's called the Radura, symbol for food that is treated by radiation. And if I find some food in the store having that sign, this is the food that I'm going to buy, because it would have basically been irradiated and bacteria and fungi killed. So it eliminates the possibility of foodborne disease. Where do we get that foodborne disease? There are several sources: Campylobacter species, the Salmonella, the E. coli 0157H7 is a new mutation that is resistant to antibiotics by the E. coli bacteria, and Listeria. The economical cost goes in the billions of dollars. 10 to the ninth dollars is the billion. The Campylobacter 1.2, Salmonella is the leading one, $2.4 billion. Chickens can be contaminated very easily with that new mutation of E. coli. When chickens are slaughtered, basically their guts, what is in their guts contaminates the meat, and if it's not well cooked, it causes lots of problems. So let's look at the Escherichia. E. coli stands for Escherichia coli infections, and that is not pie in the sky. This is an actual bacterium shown here by the CDC, magnified 10,000 times. That's from the Center for Disease Control and Prevention. And you find E. coli, in fact, in flour. And if you find it in flour, this means that you find it in bread. So it's a good idea to cook your bread or microwave it before you eat it. I'm not scaring you here, but this is reality here. The E. coli, another antibiotic resistance mutation of E. coli, Escherichia coli, ST137, has also appeared. And definitely after you go to the toilet here, you need to wash your hands. Otherwise, they spread from your guts to your food supply. We have 40,000 Americans every year getting sick of the Salmonella. This is the most common infection from foodborne disease. And unfortunately, 600 die from being infected with foodborne Salmonella of different types. And in fact, there are some bacteria that we don't know about. This is, we're talking here about what we know about. There is a lot that we don't know about. This is a scanning electron photograph of the Salmonella typhimurium. It's called, again, from the Center of Disease Control. And other type of infection is what's called the listeria infection. 16 people die basically in 2011. Listeria is also called listeriosis, occurs when people are infected with a listeria bacterium. So these are not viruses, these are bacteria and fungi. And let us just look at some bacterial agents causing food poisoning. And it is not stomach flu, all right? It's really a whole range of bacteria affecting our food supply and affecting us. And I'm telling you, this is really part of what we know. There is lots of these sources of infection that we don't know about. This is what we know about. Campylobacter is basically occurs in undercooked poultry. So if you use chicken on a maybe cooked in the backyard, you have to really have it well cooked. You get an incubation period 2 to 5 days, and then you get sick for 2 to 10 days. The Escherichia coli 0157:H7 occurred. This is a mutation of the E. coli that's undercooked, occurs in undercooked beef, raw produce, particularly spinach. Why spinach? Because in some parts of the United States and maybe some parts of Mexico, where it's imported from, in the United States, they use the feces or manure from pigs to fertilize it. And of course, that would contaminate the spinach if it is not washed. Washed is not enough, it has to be cooked. In some other countries where it's imported from, they even use human feces to fertilize these foods imported in the United States. Maybe cantaloupe, for instance, is fertilized in some countries with the waste from different cities. Listeria monocytogenes happens in deli meat, hot dogs, and pasteurized dairy. Don't dare, that's a pun intended here, don't dare having any dairy that is not pasteurized. Salmonella occurs in undercooked eggs. That's why I suggest that you cook eggs on both sides and avoid eggnog around Christmas if eggs that are not cooked is used in them. poultry, and peanut butter. In fact, has that salmonella in the peanut butter. You can get sick for 7 days. Shigella happens in raw produce egg salad, 4 to 7 day duration. Staphylococcus aureus happens in meat, potato, and egg salad. Yersinia enterocolitica, undercooked pork, and that can be very serious. It can last for 1 to 3 days of sickness. So maybe you may want to favor beef to pork in that case. Pork meat is particularly hazardous. It also contains a parasite, Trichinella spiralis. The abbreviation for it is trichinia. It is often found in pork products. The larvae of the parasite are destroyed by cooking, by radiation, or by keeping the meat below freezing for over 20 days. This can lead to serious sickness, even though it is common. This is the origin of the avoidance of pork products by the ancient Egyptians. That's when pork was banned in the food supply all the way to the time of the pharaohs. A smarter addition that is busy continued by both the Jewish and the Islamic faith. Pork is not well cooked, it is a big danger. So what do we do about this? Well, radiation helps us reduce the damage from all these food products. So we are not just threatened by viruses like the COVID-19, we are also threatened in our food supply by the occurrence of bacteria and fungi. So irradiation would come to our help. It is helping us to a certain degree with the sterilization of medical products and, of course, the pasteurization of some foods like milk. I wouldn't think about using milk that is not pasteurized. More than 35 countries worldwide allow the irradiation of food. In the United States, in addition to raw beef, pork and lamb, spices, wheat, flour, potatoes, pork, poultry, fruits, and vegetables have been irradiated. Especially products like spices that are imported from other countries. Irradiation was approved to control trichinia, that's in pork, in 1990, salmonella in chickens in 1994, and E. coli in raw meat in 1999. In Canada, irradiation is used to prepare meals for hospital patients. So that protects them really from dying, not from the cause of their admission to the hospital, but also from a disease that would be brought to them in the food they eat. Cancer patients in particular cannot tolerate a dose of E. coli. That would kill them immediately. French food processors also use irradiation. The World Health Organization designated food irradiation as a perfectly sound food preservation technology that is needed in a world where foodborne diseases are on the increase and where in between, as I mentioned earlier, 1/4 to 1/3 of the food supply is lost after harvest. We can increase the food supply in the world by 1/3 by irradiating the food. How do we irradiate the food? We have two methods used to irradiate the food. One uses gamma ray irradiation. So this is electromagnetic radiation. And the two isotopes that are particularly used in that case is the cobalt-60 isotope. Remember, it was in the table that I have shown you in the previous chapter. Cobalt-60 pencils. Cobalt-60 is a very powerful gamma emitter, and gamma rays, electromagnetic radiation, can deliver a dose of radiation to the bacteria or the fungi and kill them and make the food supply much more safe to consume. Another gamma emitter is a fission product. Cobalt-60 is produced, by the way, by getting the metal cobalt-59 and simply place it in a nuclear reactor. When you absorb the neutron in it, it becomes cobalt-60. Cobalt-60 also has been used in what were called the cobalt bombs in hospitals, where you place it in a lead enclosure and then use the gamma rays to treat cancers in people afflicted with cancer. Another isotope, cesium-137, also emits very powerful gamma rays, has been used as a gamma ray source. So two sources really use electromagnetic radiation as very powerful gamma rays. Another approach is to use high energy X-rays. So the energy in that case is not in the million electron volts, range like cobalt-60 or cesium-137, but it is in the kilo electron volt of X-rays. How do you generate X-rays? You accelerate particles like protons and hit the target of heavy element like tungsten. And if you hit the target of tungsten, you can produce X-rays that are very powerful. Actually, it's linear accelerators that accelerate electrons. So an electron beam interact with the heavy element, the tungsten, and produces gamma rays. So they have an irradiator, say, in Saint-Gobain in France, and it's also used experimentally at Iowa State University. So that's in our future to be using more in the United States. This is a schematic of a typical gamma irradiation facility. As I told you, it is used routinely now for any medical product, for the sterilization of medical products. So in that case, you have the syringes, plastic disposable syringes in boxes, but you can also use the gauze used in operations or plastic tubing used in medical applications. They are inside boxes. The boxes are simply closed. They are not subjected to any kind of heat. You put it on a conveyor belt. The conveyor belt goes through a maze of a very, very, very thick concrete structures because the concrete is a good shield against gamma radiation. As the product is loaded into a conveyor belt, you would have a storage pool where sources of gamma rays are stored, like cobalt-60 or cesium-137. And usually they're stored underwater. Water is a very good shield against radiation. When the process of irradiating the food supply, in that case, or the medical products is going on, you raise the cobalt-60 from under the water in an irradiation room, and the boxes of the product go in between the sources of gamma radiation in that case. And it could be food like potatoes. In fact, in Canada, the potatoes are irradiated in a large truck that goes to them in the field. And in that case, fungi on the potatoes, and in Europe on strawberries, maybe the fungi are killed, and that extends their shelf life. And never eat onions or potatoes that have sprouted in your garage. So you buy the stuff and it sprouts, because when it sprouts, it generates Prussian acid and it's extremely toxic. If you eat sprouted potatoes, you can get very sick. It's toxic. The Prussian acid is toxic. So you raise the radioactive substances here. The containers of the boxes of food supply or medical product goes in between the gamma radiation and exits on another conveyor belt here, and you unload it without really any human touching it in general. This technology has been used and developed by the military to a great extent in the meals ready to eat that the military use in the field. So this is a picture of a water shielded irradiator configuration. You place the plates of cobalt-60 or cesium-137 underwater. You have a control panel on the top. You can stand there and look down the water. The water acts as a very good shield in general. So just water is used as a shield. And this is a picture of cobalt-60 irradiation source underwater. If it is underwater, you'll find that the cobalt-60 emits a beautiful bluish color in the radiation. And this is what is called Cherenkov radiation, where the electrons emitted move at faster than the speed of light in water and emit that beautiful Cherenkov radiation. So this is underwater, it's well shielded. You raise those plates up, and in that case, you sterilize the food supplies. This is an irradiator, in fact, used by the United States Army NATIC labs, food irradiator, and to irradiate the meals ready to eat. It is unthinkable to give astronauts food that has not been irradiated, because you don't want them to get the stomach flu on the spaceship. Imagine just what would happen if they do. So they depend on irradiated food, either by X-rays from electron accelerators or from gamma rays. This is how the military irradiate their meals ready to eat. You don't want your soldiers to get sick on the battle, under battle conditions in general. All right, now the question is, what is the engineering here? The engineering is how much radiation to deliver to a food supply, or in that case, we know the amount already for medical products, but for the food supply, how much energy, how much dose of radiation do you deliver to the food to reach certain levels of sterilization or pasteurization in general? For this purpose, we are going to estimate the amount of energy that we deliver to any material. And that material could be plastic, could be wood, could be food. It doesn't have to be a living creature like humans or a plant or an animal. So it could be just any material. So in that case, strawberries or plastic in a disposable syringe, the amount of energy that you deposit into it is proportional to the level at which you are destroying those fungi, and that can be harmful to people in general. You'll find that we define in that case in the SI system of unit, the Sistema International unit that we call the gray. The gray is abbreviated as G sub Y, because of Mr. Gray was one of the pioneers in studying the effects of radiation. 1 gray is the delivery of 1 joule of energy per kilogram of the material. Later on, in another chapter, we'll specify if that material is a living matter. This here is any matter, whether it's living or not living. So 1 gray is the delivery of 1 joule per kilogram of the material that is subjected to radiation. And 1,000 gray is what we call 1 kilo gray. And you'll find that depending on the dosage, let's say 7 kilo grays for frozen meat, you'll find that 4 kilo gray up to 7 kilo gray can sterilize the meat from any kind of bacteria that would cause harm. In the conventional system of units, we use the unit of energy as the erg, and the unit of mass or weight as a gram. So when you take 100 ergs per gram is what we call the radiation absorbed dose. RAD is the abbreviation. So in the conventional system of units, the unit of dose is the rad, and in the SI system of units, the Sistema International, it's the gray. And then there is a relationship between the two, is that 1 gray is equal to 100 rad. So it's convenient to remember that 1 rad is 1/100th of a gray. So 1 rad is 1 centi-gray. I like to remember that relationship because you'll find that the gray and the rad are used interchangeably in practice. People still stick to the CGS system of unit, the unit of the rad. Fresh vegetables, including avocados, celery, bell peppers, broccoli, basically would need 1 kilo gray of radiation to increase their shelf life. They can remain on the shelf without spoiling in the stores. As I suggested, 1/4 to 1/3 of our food supply is lost to spoilage in the United States. Different levels of radiation achieve different levels of protection for our food supply. The lowest level is pasteurization. This is accomplished with low doses of radiation from 2 to 5 kilo gray. And this is used for prolonging the shelf life or storage time. So if you pasteurize the milk and you place it in your refrigerator, it will last there only for a longer time, but eventually one single bacteria starts propagating and will destroy it. So this is at the level of killing the bacteria and the fungi of 2 to 5,000 grays. Sterilization is a higher level of protection of the food supply. In that case, that requires 10 times as much energy dosage than the pasteurization only. That's 20 to 45 kilo gray. And in that case, it allows you long-term storage without refrigeration. Isn't that amazing? And that's why the military use it in the meals ready to eat. And that's why the astronauts in space are fed food that has been sterilized. Different foods need different levels of radiation doses to be sterilized. For instance, potatoes and onions need to inhibit their sprout or their sprouting in storage from 0.04 to 0.1 kilogray. And remember, the gray is energy per unit mass, so that's already per unit mass. Grains and cereals need from 0.2 to 0.5, and that kills insects. As I remember, we lose 30% of our food supply also in grain to what? To beetles and maybe even rodents like rats and mice. Fruits need 0.5 to 3 kilogray. That sterilizes the larvae of lodging insects. So in that case, whatever fruit you buy from the store would last longer because there are no bacteria to start feeding and spoiling them. Fish, 2 to 8 gray, extends the shelf life up to 30 days. And this is a prospect for the fishing industry. Instead of loading the fishing boats with ice to store, to protect the fish that they catch from spoilage, just having an irradiator would, with 2 to 8 kilograms, can extend the shelf life of fish up to 30 days and not have the fish spoil. Spoiling means, of course, you lose the food supply, but worse, if bacteria are allowed to grow in the fish, then it can cause disease. So that's saving lives and saving the food supply for the well-being of those who eat it. Meats, beef and poultry needs a much higher dose, 45 to 56 kilogray. But then if you store it just in a plastic container, in a plastic kind of storage kind medium, you can store that food for 1 year at room temperature. You don't need refrigeration in that case. So it's amazing in how it can save us both the 30% of the food supply that is lost, and at the same time also protects us from disease in general. Unfortunately, you'll find that still lots of different chemicals are being used in the United States. For instance, the Florida Citrus Commission basically use methyl bromide as a quarantine treatment for citrus fruit. So when you drink orange juice, you're being subjected to some methyl bromide, even though it's not listed in the contents of the juice container. You could see here that you can extend the shelf life of strawberries. That's been done in Europe and in Canada, but I don't think it's done in the United States. So you irradiate strawberries with 2 kilograms of radiation, and you could see here that 2 samples of 2 different an irradiated food here and a non-irradiated food control for strawberries. So it extends the life of the food supply. There are risks and benefits of food irradiation. Remember that case, this is the decay graph for the cobalt-60 isotope. If you go to the chart of nuclides, you can obtain it. You'll find that cobalt-60 has a half-life of 5.26 years. It emits a beta particle that goes to the excited state of the isotope nickel-60. So cobalt-60 becomes nickel-60, but after the release of gamma radiation, this one, that gamma photon here is 1.33 million electron volt of energy. This gamma photon is 2.1 million electron volt of energy. This one is 2.5 minus 1.332. Those gamma radiations basically sterilize, kill the bacteria, the fungi, or the insect. I mentioned cesium-137. That one has a half-life of 30 years with lower energy gamma rays. That's 0.6 million electron volt here, reaching the ground state, and this one is 0.28 million electron volt reaching the ground state. This is a table of the gamma rays energies from different isotopes in general. Okay, so we are coming to the end of the lecture here. We may use sometimes natural sources of gamma rays like thallium-208 in the decay chain of uranium that is not being used. And I am talking here about future developments for those of you who are entrepreneurial and want to find some interesting topic to develop new technology. If you go and search the web for how our grain elevators here in the Midwest, around, say, go to Tolono or to Sadorus, you'll find those big structures where grain, corn, soybeans, and wheat are being stored. Now, they are subject to all kinds of fungi growing in it and also insects like beetles feeding on it. Now, it's a competition between humans and the insects and the fungi and the bacteria for the stored food supply. So what do? They really fumigate the stored grain. And basically, also when the grains are shipped to other countries in the world, in the ship holds, they are fumigated. The word is fumigated. And the fumigants are solid chemicals. And if you go to the internet and do your own research, these are some of the materials that are used to fumigate. Fumigate comes from fumes, from the French fumée. Those solid compounds basically release gases to kill the bacteria, the insects in the stored grain. They use the following: phosphine, PH3OS, methyl bromide, sulfuryl fluoride, chloropicrin, methyl isocyanate. We see the word cyanate, that is toxic, that's a poison. Synergized pyrethrin, this is from the chrysanthemum flowers, and aluminum phosphide. All these are poisonous. And imagine that all those materials are toxic materials that get into the corn, the wheat, and the soybeans as in the basis of our food supply. So without knowing it, we eat bread that contains some very toxic substances.